Hi YouTube! It's been a week since my last video and I've been working hard, so I've got a bit more to show today than usual. Here's an outline with timestamps. First off, engine improvements. I've been working on something I call unique components. So I haven't really mentioned this before, but I've implemented my own ECS for this engine. I'll make a future video about that. There are many gameplay-specific ECS systems where it makes little sense to have the classic ECS split between system and component. When I started working on player movement, I realized that I was painstakingly passing the current component by reference into every single system function. In this situation, I would much prefer to be working in the component directly. Therefore, I made a new base component class called unique component. This class has the same functionality you would expect from a system, except in the scope of itself. There is still a system that owns this component type, but it is not exposed to the implementer. This means that I'm going against one of the core principles for the ECS approach, that components are just data that systems manipulate. But it's my code, and I can do whatever I want. Plus, I think that for player components, such as movement, I'm allowed to make some exceptions. Anyways, this is completely optional. The classical system component approach is still there and is going to be used most of the time. I've added system priority. It's important that some systems update or initialize in a particular order. To enable this, I've added a priority function which will be used to sort the systems. Constant properties. There are some properties that should only be editable using the UI or when loaded from file. This means that they should not be editable in the normal code. To enable this behavior, I've added a middle step called constant property to my property class hierarchy, where only constant getters are exposed. These properties are declared like this. Smart pointers. I have made my own smart pointer implementation. Some time this week was spent testing this, as there were some strange edge cases that I had to figure out. Scenes. I have been working a lot on scenes. What is the purpose of a scene in my engine? A scene is a collection of objects that can be saved, loaded, and edited. Every scene object can be based on a blueprint and can override any data. This means that there must be a scene resource that can be instantiated into a scene instance. The scene instance can be destroyed, bringing with it all of its instantiated entities. An important detail is that I do not think an object has to be part of a scene, and that scene instances can be owned by any object and passed around by a copy. In addition, I'd like for scenes to support origin shifting, meaning that a transformation is applied to all the scene objects. It might not be worth explaining the code for this, since it mostly has to do with handling deserialization overrides, but it's in the engine and it's working. Collision callbacks and queries. Last time I said that I had to implement collision callbacks. I spent some time this week implementing this, and it's now working. I can detect collisions and overlaps, and this is forwarded to the correct system. I also implemented trace and sweep scene queries. The biggest challenge with this was to figure out the interface and how to keep this code out of the main physx manager. For queries, I implemented a query class, which has some static functions and is friends with the physx manager. Types. Unfortunately, C++ is not made for working with types. Reflection is a challenge, and some behavior is undefined on some platforms. There are still situations where types are very useful. Type ID is often used when working with types, but my opinion is that calling type ID t #code is not very nice, and passing around a type hash as a size t is not very nice either. The purpose for my type class is to wrap this functionality and provide a nicer interface, for more readability. Here is the core functionality, but the class is not very useful without its interface. Editor improvements. New file browser. I wasn't happy with the look and feel of the previous file browser. There were many quirks when navigating, and you couldn't set the default path or the root folder. I therefore decided to create my own, which looks like this. I have published this on GitHub. Inline resource editing. When editing a blueprint, I found myself often needing to open external assets and edit their JSON manually. I therefore made it possible to edit these assets inline. In this example, you can see that I have assigned a physics material file called pmDefault, but that I can edit the material parameters directly. Raylib and rendering. First of all, a new raylib version was released, raylib 5, and I just had to check it out. Instance rendering. Meshes with the same material will be batched and rendered using instance rendering. This is done by converting the mesh and material resources to a hash, and using that hash for a fast map lookup, where each entry contains a vector of instance transforms. Default shading. I have investigated how to work with shaders in Raylib, specifically how to send uniforms to the shader, as well as which uniforms are set by default. I'm not a big fan of not knowing which uniforms are set by default. I'd like to manually control this. My first step in this process was to try and calculate world space normals for any object, which I did through trial and error. After that, I could easily make some shading that will help with distinguishing shapes. Gameplay. StateMachine. StateMachines are a great fit for many gameplay systems until you start setting up transitions. So how can we avoid this? My solution is simple. A transitionless state machine. Haha. But I hear you say, some systems require transitions. In that case, you have two options. Calculate the transition automatically, or you should use another type of system, and not a state machine. Anyways, my state machine is simple. There are two classes to know about, the state machine and the state. The state looks like this. Check. This function will be called every frame and returns the state that this state thinks should be the current state. Update. This is the main update function and will only be called on the current state. And this is the state machine. It contains a collection of states and the current state. Here's the core of the state machine. It's very simple. First, we check the conditions for every state. Some states might want to transition. Because states is sorted, this will be prioritized based on state priority. If a state wants to transition, do that. Then, update the current state. This state might want to exit, in which case, do that. Here are some important getters. This is pretty straightforward. The most interesting function is try_override_state, which is like setState, except it will only override if the priority of the new state is equal or greater to the current state. Player movement. With the state machine, I made some more advanced movement than the basic add force. There is an idle, run, and air state. I would like to show you how these states are set up for this. So this is the idle state. Idle does nothing. Then we have run. In check, we transition to run if on ground and moving. In update, we go back to idle if no longer moving. This is air. In check, we transition to air if in air. In update, we go back to idle if no longer in air. And with this, and some behind the scenes movement code, the player can now move around and jump in a way that I'm pretty satisfied with. There is separate air and ground friction, acceleration, and max speed, giving me more precise controls over the feeling. Alright, that is it for this week, I guess. But I will see you guys around.